Jnanam paramam dhyayam. Knowledge is supreme.
So far we looked at a particle trapped inside a box due to this potential which is infinity at some boundaries. If you make that potential energy to be finite, what are the new features you start seeing? And what is the new solution? These are questions you can ask. This also you have done in the context of one-dimensional potential wells, right? What do? You break it up into region 1, region 2, region 3. Region 1 and region 3 are almost similar, and region 1 goes up to minus infinity, region 3 goes up to positive infinity, and you have an intermediate well region. And if the energy which I have marked as C is less than U, then you can have a kind of a, classically it would have been, if the particle was inside, it would have been inside, right? Why? Because the total energy has to be, cannot become less than the potential energy. If such a thing happens classically, you get kinetic energy to be negative. Kinetic energy negative in classical physics, is it allowed? Not allowed. But in quantum mechanics, because we are going to take this to be like it is inside the well with energy less than the potential energy, and it is like a wave, there are chances of the wave trickling out into region 1 and region 3. Okay. So, this is what I am saying here. Take the energy of the particle inside the well as E, which is less than the potential energy which is seen in region 1 and region 3. And now we would like to see this in classical mechanics. The particle cannot penetrate the two walls x equal to 0 and x equal to L because of finite energy. The earlier problem, particle in a box, is you made U tending to infinity. Now I made U to be finite. But quantum mechanically, you will get non-zero wave function in region 1 and region 3. You all agree pictorially? Okay. So, this is what I said. Quantum mechanically, there is a certain probability of penetrating into region 1 and region 3, even though the total energy of the particle is less than the potential energy. Okay. So, you can plot the wave function. The red line which I have plotted, the red line is actually the, what is that red line? Particle in a box with infinite potential energy, ground state wave function, right? Everybody agrees? Sine function. It goes to 0 at x equal to 0 and x equal to L. And what happens? So, this is just to be taken as not an accurate answer to the differential equation. The trend of the wave function, once you make U to be finite, is that it tapers off in region 3 and region 1, and it is not 0 at x equal to 0 or x equal to L. And it takes care of what all properties? Continuity of wave function and derivative of wave function to be continuous. It will take care of that. Earlier when we did the particle in a box, we didn't need to worry about it. Is that correct? So, some of these things when you see visually, some of these plots, it will register in your mind much better rather than mechanically solving equations. So suddenly the particle in a box, I suddenly reduce the barrier from infinite barrier to a certain height. And what all can happen? If you plot the ground state wave function, start showing some tails in region 1 and region 3. Okay? What happens to the wavelength? You can start looking at what will be the de Broglie wavelength of the particle in an infinite dimensional box. Take a ground state of the particle. What will happen to the wavelength of this? Pictorially you can see wavelength, what happens here? Increasing, right? The periodicity of becoming 0, it is L in the context of the particle in a box, but it's no longer L, it's more than L. So the wavelength starts increasing. If the wavelength starts increasing, what will happen to the energy? Energy will start decreasing. Then you can start arguing without even, can get a qualitative way of feel of what happens in realistic situation. Okay? Okay, so then the math, formal math which you have all done, region 1, region 3, you put E less than U, right? I'm sure you have done this. And you take then, since E is less than U, E minus U is negative, you call it as a negative A squared. And then you can solve this differential equation. The solutions are exponentially growing and exponentially damping solution in region 1 and region 3. Formally write it as AE par AX. I'm going a little fast because the assumption is that you have done these things. Just for you to recall, I'm going, okay? It's not that this is not the theme of quantum mechanics 1, but you need to know this if you want to do quantum mechanics 1. So I don't want you to forget. So that's why I'm going through this. Okay? So region 1 and region 3, formally this is a solution to the differential equation, but you will start putting in condition that the wave function cannot blow up in these regions, right? So that comes from physics. So once you put in the condition that the wave function cannot blow up, which coefficients will vanish? And region 1, as x tends to minus infinity, the one which will kind of blow up is the second term. So you can make the B coefficient to be 0. Similarly, for the region 3, which one should be 0? C should be 0. Okay. So this is the physics input. The solution which you wrote in the top, this is blindly looking at a differential equation, you will write the solution. Okay. But the physics input is that you need it to be well defined in the appropriate region. Will tell you which coefficient can be put to 0. B will be 0 in region 1 and C will be 0 in region 3. Okay, so the meaningful solution for region 1 and region 3 is psi 1 of x is AE par AX and psi 3 of x is DE par minus AX. What about region 2? Region 2 is exactly similar to what you did for a particle in a box, because inside the box U is 0, so you can solve them, which is a sinusoidal function. But since the wave function is not vanishing at x equal to L and x equal to 0, it will be in general a linear superposition of the two solutions. You can't make G to be 0 in this case. G can be arbitrary. Agreed? And then you put in boundary conditions. Continuity of wave function. What are the two boundaries? X equal to 0 and x equal to L. At x equal to 0, 1 and 2 should match, and at x equal to L, 2 and 3 wave function in the region 2 and region 3 have to match. So at x equal to L, region 2 and region 3 wave function and derivative of the wave function, because the potential energy is finite here. When the potential energy is finite, both wave function as well as the derivative of wave function should be continuous. Okay. So, this I have already said. How does the wavelength compare with the particle in an infinite well? You already plotted here, and you can make out that the energy eigenvalues, how will it be in comparison to energy eigenvalues. Okay. So, this is all clear from the picture. Just for completeness, time dependent wave function, how does one do it? You try to write, we will take only potential energies which are functions of only x. Okay. This is the kind of problems you are going to look at in this course. But you could have time dependent potentials also, we will see it in the next course, okay, the next level course. In this course, you will be only a function of position, and we, in one dimension, we will take it to be a function of x. Wave function can be in general a function of x and t. Because potential energy is only a function of x, looking at the differential equation, you can separate operators which are dependent on time dependent operators from the space dependent operators. So, you can write your wave function as a product of psi of x and phi of t. Exactly like what we did in a two-dimensional box, I just want to mimic here for a time dependent wave function. So, you remember the time dependent wave function, the time dependent Schrodinger equation, we can rewrite it in this fashion, right. This part is the IH cross del psi of xt by del t will become dependent only on phi of t. So, you can write it as the partial derivatives as total derivatives of phi of t, and you can divide it by the wave function and write this as two separate operators, operators which depend only on t, operators which depend only on x, and you can equate it to energy E. So, from the time dependent Schrodinger equation, show the step. Please work it out and show the step. And from this equation, you can solve this to be equal to E. This equation, the extreme left to the extreme right, you will get the time dependent piece of the wave function, okay, which is dependent on the energy of that energy E. Okay. So, what will be the total wave function? For potentials which are only position dependent, the total wave function can be written as psi of x, where psi of x is the solution for the time independent equation, and the time independent equation will also have, the state will have a specific energy E, right, and for that energy you will have an exponential factor which is time dependent multiplying that piece. This is the most general solution for time independent potentials. Yeah, and this psi of x satisfies time independent Schrodinger equation, and you can show for such cases where you have, they are called stationary states. If you do mod psi of xt squared here, it is same as mod psi of x squared here. Is that clear? Because this is just a phase factor. So, such states which satisfies this property, they are called stationary states. Are superposed states stationary states? Suppose I take a particle in a box and take the state to be a superposition of ground state and first excited state. Are they stationary states? No, they are not stationary states. Particle in a two-dimensional box, if I take a superposition of degenerate states, what happens there? Will that be stationary states? Think about it. So, the energy will be the same. So, it will be looking like a stationary state. Okay. So, some of these things, once you go to two-dimensional, the stationary states can also be in the subspace, where it can be in the superposition of degenerate states. Okay, so this is also one of the important feature which happens in experiments, which is called tunnel effect, which requires quantum mechanics. You can't work with classical mechanics to explain tunneling, which is seen in the lab. And we have seen infinite potential well and finite potential well problems so far. Also, we have seen time independent potential energy, how to write the time dependence for them, is to summarize. So now what do we want to see? Even if the particle does not have enough energy to cross the barrier, you can still tunnel through this. So this is what I showed for your finite, for the finite well I showed you. If suppose the energy of the particle is E and U, where E is less than U, the wave function can actually cross, it can tunnel into region 1 and region 3, okay. You can also have a similar situation in the context of barriers, where the energy of the particle is less than the energy of the potential barrier. Suppose you want to climb a mountain, okay, and you don't have that much of energy to climb the momentum, you don't have that momentum or energy to climb the mountain. Classically we cannot. Only if you have that much of energy to go against the potential energy, then you can go. But quantum mechanically, there is a microscopic particle, it can start showing signature going into the other side. Okay, so this is what will happen in microscopic world. Not for macroscopic world, as I already said, the wavelength is so small that those signatures are not going to be seen. The wave-like nature is not going to be seen, right? Okay, so take an electron with energy E less than potential energy, and then tunnel effect is seen experimentally. That what does that mean? Classically, if I shoot in a particle or a beam from region 1, will I see it in region 3? No, classically I cannot see. Quantum mechanically we do get some kind of a signal coming out of region 3, even though the energy of the beam which I sent in is much less than the potential energy of a region which I have put in. Okay. How do I put in such kind of a potential energy region? I can try and make a constant electric field. I can put in some region between x equal to 0 to x equal to L. I can make a non-trivial potential energy region. Okay. So this particle which is coming here or a beam which is coming here will not be able to cross that region because of the, it will not have that enough energy, but quantum mechanically it can tunnel through it because there will be a damping wave function and it can come out of it. Once it comes out of it, it is like a free particle again, it can move. Okay. So this is the trend qualitative. So similar to what we did in the case of potential well, you can solve region 1, region 3. Region 1, region 3 is like a free particle, u equal to 0 situation. So you can write the solution as a linear combination of the free wave, which is oscillatory solutions. And what are the interpretations of those terms? In region 1, the incoming wave is going along positive x direction and the reflected wave is going in the opposite direction, right. So B is the factor multiplying the reflected wave and AE per IKX is the incoming wave. And region 3, what is your expectation? The incoming beam goes in Even though the intermediate region has potential energy higher than its energy, it kind of exponentially tapers inside. After that, there is nothing to reflect it back. It has to keep going. Okay. So, you will have only a forward wave, which is what is called as a transmitted. Mathematically, you can write a linear superposition, but looking at this qualitative situation of an incoming beam coming from the left, facing a barrier whose potential energy is greater than the energy of the incoming beam, kind of exponentially dampens down in region 2, and when it comes out, there is nothing to reflect it back, it keeps going. So, that is a transmitted wave. Okay. So, I have shown it pictorially also here. So, there is an incoming beam. When it faces this barrier, there can be a reflected beam, but inside this region it keeps exponentially damping, and again when it comes out here, it goes in the forward direction, which is the transmitted beam. Is the picture clear? And what does the experimentalist want to see? They want to see the signal in region 3, and they define a quantity called the transmission amplitude or transmission coefficient or transmission probability, capital T, which will have information about the probability of the particle seen in region 3. In fact, it should be explicitly the flux which is seen. You will define what is the flux, and that ratio with respect to the incoming beam, which is just the forward incident beam, which depends on the coefficient A. Okay. So, that ratio is what is called as a transmission coefficient. Conservation will tell us if the transmission coefficient T is found, there will also be an equivalent reflection coefficient. There is a reflection beam. If a detector is placed in this region also, it will get a reflected flux, and that will give you a reflection coefficient or reflection probability R, and total probability has to add up to 1, conservation, which means R plus T should be equal to 1. So, that's a way to understand. And tunnel effect is proven because T was non-zero, and they said that tunneling happens in quantum mechanics and not in classical mechanics. Classically, T is 0. In region 2, you will have a non-trivial potential energy in the barrier, and you will have what kind of solution? I have already said it should be an exponential damping or growing, because it is in a compact region. So, you can rewrite it as an exponential solution, and the particle does penetrate the barrier, can emerge in region 3 or region 1. Can plot the curve which is of this type. Okay. So, this is just a linear superposition of exponentially growing and damping. You can have both the linear combination, and you should have at this point continuity of wave function and differentiability of wave function. Similarly, here continuity of wave function and differentiability of wave function, and this is a plot of the trend of how it will be oscillatory on region 1 and region 3, and it will be exponentially damping or growing in region. Okay. So, this is just a part of the earlier one. You just have a potential step, and you can particle is coming from region 1. If the energy I have shown in the diagram as E above U, which means E is greater than U, okay, which means what is the type of solution in region 1 and region 3? Region 2? Sinusoidal. You will have it to be an oscillatory solution, and you will have solutions in 2 regions will be oscillatory, and the particle is not, there is no confinement. Particle in a box, the particle is confined to region 1 and inside the box. Here the particle is free, it keeps moving freely, and once it sees this potential energy, it will show a slight deflection because its energy minus the kinetic energy will decrease, right. That is all will happen. Otherwise they are free particles, and you have region 1 and region 2, and you can interpret these terms as incident wave, reflected wave and transmitted wave. Okay. Can we have D? Is D allowed? D is not allowed if you take the incident beam coming from the left. Similarly, if you take the incident beam coming from the right, yeah, so you have to make sure that this appropriate coefficient is set to 0 depending on the problem. Okay. So these two solutions which are given are two solutions of the differential equation, but which one will be dependent on, if I say the incident beam is coming from the right, then you have to appropriately put this, only the transmitted beam will be allowed in regions. Okay. And boundary condition, derivative of boundary condition, see how the de Broglie wavelength compares in region 1 and region 2. Okay. And do a similar exercise for E less than U. Okay. You will have a, if E is less than U, then in region 2 it will be an exponentially growing and damping, but because region 2 goes up to plus infinity, you have to put C equal to 0, right. Very systematic. Nothing, it's not that today this will be the answer, tomorrow it will be a different answer. It's the same going to be. It's logically argued and fixed. Okay. Okay, so what is a bound system? Bound system means what? It is kind of constrained into a region. Like particle in a box is a bound system. What about harmonic oscillator? Harmonic oscillator has some kind of potential like this, right? If there is a particle with energy E, okay, there are classically these two are turning points, you all agree, right? Beyond that point it cannot go because its kinetic energy will become negative, right. So typically it is going to be some kind of a bound system where the formal definition of a bound system is if E is less than V at plus infinity and V at minus infinity, we call it to be a bound system. Particle in a box satisfies this. Harmonic oscillator satisfies this. So they are all bound systems. What about hydrogen atom? What about hydrogen atom? Hydrogen atom, what is the potential energy? Is that right? What happens for R tending to infinity? So condition for bound state is E less than V at R tending to infinity, which means E less than 0 are bound states. All your hydrogen atom spectrum energies are negative or negative, right? Suppose I make E positive, what are those states called? Louder. Scattering states. E greater than 0 hydrogen atom are called scattering states. Okay. What is the condition for scattering states? In general, if E is greater than V at plus infinity or V at minus infinity, then scattering state. What is the condition for bound state? E less than V at plus infinity and V at minus infinity, and we call it bound state. You can also see it by drawing a barrier. You can draw barriers like arbitrary, something like this, and see if you have a particle with energy, let's say this one. Okay. When it comes to this point, it may not be able to, if it is really a big peak, it may not be able to climb, but it can still come out. Okay. It's not getting trapped. So this is why it is a scattering state. And if you have a particle in infinite like things and you have a particle here, it gets trapped. When it's coming here with energy E, it can't climb up, and it is going here, it is also, you cannot climb up, so it's kind of trapped. So that's a bound state. Okay. This picture is very nicely given in Griffith's chapter 2. You should see it, the turning points and how to get it. So once you have things in a picture form, what is a bound state, what is a scattering state, why E less than 0 for a hydrogen atom is a bound state, why E positive will be a scattering state. It's nice to get a picture like this. So far you did only step potentials with constant potentials and so on. But harmonic oscillator is the first one which is going to be a non-trivial. So this is a plot of V of x versus x. Okay. So such kinds of potentials are also possible. Need not be sinusoidal. You would have all kinds of potentials. So if you have these potentials, the way to see it is first look at how the potential goes at plus or minus infinity if you are doing a 1D problem. If you are doing the spherical coordinates, then you can look at how the trend is at r equal to 0 and r equal to infinity and see what is happening. And this decide whether the solutions, what is the regime of energies where the solution will be a bound state, what will be the regime where the solutions will be a scattering state. Okay. Okay, so let's get to the bound system. So I've kind of convinced you that it's confined to a region. Particle in a box is a bound system. Harmonic oscillator is also a bound system because the energy of the particle is always going to be less than the potential at infinity plus or minus infinity in the 1D problems. Okay, right? So they are all bound systems. Formally, you can write one-dimensional harmonic oscillator where the force is proportional to the displacement, and from there for conservative systems you can find what is the potential energy and you get V of x equal to, okay, can fix the boundary condition and fix the constant to be 0. So far we did potential energies which are, even though it is x dependent, it was constant in certain region, it was 0 in certain region, but we never did problems where V of x is different at different x. Okay. So this is the x dependence, which is the simplest problem we always see in any system. Even if you take any system with potential, you can try to expand that potential energy in a Taylor series, the first non-trivial term will have an x minus x naught squared multiplying some function v double prime. So, in some sense, very close to certain regions you can see it to be like a harmonic oscillator, and harmonic oscillator potential that way is very important to know how to solve. Okay. And potential energy is independent of time. So, you can write your wave function as the time dependent piece as a phase factor multiplying psi of x, and you can try and solve the Schrodinger equation. So, what are the requirements? The wave function should be well defined, should not blow up. So, as x tends to 0 or x tends to plus or minus infinity, the wave function has to go to 0. This is what you did in your last year course. You took a functional form, and this functional form has this property that as x tends to plus or minus infinity, it goes to 0. You all agree? Provided a should be negative. Okay. So, for n equal to 0, take f naught to be 1 and check whether it satisfies the equation, and then you can figure it out. You can do a convenient change of variables and solve this and put in this condition that I have just made a change of variable for just the equation to look more better, nothing else. Okay. So, alpha and rho makes the change of variable look better, and you can neglect alpha in the above equation. You can further make a change of variables so that it becomes a familiar equation whose solution can be found. What is the solution to this equation? E to the power of minus half t plus or minus half t. Okay. So, I will stop here